Okay. Hi everyone, welcome to our session. Today our session is about the big ideas for HPC education. We are here with our speakers, so I can introduce them. So this webinar will cover the existing needs in HPC training to recommendation for instructional design. Our authors of this study, this white paper that we will share later in the chat for you to be able to look at it, are Eleonora Barelli, Head of Education and Foresight from IFAB Foundation, and Michael Lodi, Junior Assistant Professor from Department of Computer Science and Engineering, University of Bologna. So thank you very much for agreeing on this webinar, and I'm leaving the floor to you to start. So just a moment to stop sharing. Please go ahead. Thank you very much and enjoy the session.
Thank you, Sima, for the introduction, and thank you all for being here today, hearing from us for the research that we conducted. First of all, I share my screen, but I want to say that this is actually an ongoing work. We have produced a white paper that is published, that is freely usable, and that we hope you will find interesting and source also of design of new projects or ongoing ones in the field of HPC education. So it's something that exists, and we will present the state of the art of our work now, but we will end our talk with the call to action, since of course we want to leave this kind of research open also to suggestion and also to the advancement in technology that is very, very important in this field. So Sima already introduced us. I am Eleonora Barelli. I work as the responsible in IFAB Foundation for the area of education and foresight. I am a physicist as a background, and I have spent 6 years in research at the University of Bologna in the field of physics education, specifically in the field of computational sciences education. So now it's this kind of background that inspire my research. I ask Michael Lodi also to present himself now.
Yes, hi everyone, and thank you for the invitation. I'm Michael Lodi, assistant professor at the University of Bologna. I'm a computer scientist, but since my master's degree and then in my PhD, I've always worked in computer science education, which is, at least in Italy, a very young field of research. So I covered a lot of different topics, mainly to research in how to introduce programming, introduce more advanced topics like cryptography, and now I'm also working on high performance and quantum computing education. I'm young in this specific field, but this work with Eleonora was the opportunity to dig deeper in this kind of approach, bringing my expertise as a computer science education researcher. And so in this talk, I will bring in particular a theoretical perspective on the big ideas in particular that I hope can be useful not only for HPC, but in general in education and professional training and so on and so forth. So.
Thank you, Michael. And we come exactly to the agenda of our talk of today. I will briefly introduce you the research context in which this research was positioned and was born. Then I present one of the results of the work, meaning the emerging training gaps in the HPC education that our research has revealed. Then I will pass the floor to Michael Lodi in order to present our framework that is the main original part of this research that is bridging the theoretical framework of big ideas to the field of HPC education. And we will present, of course, the 10 big ideas that we identified in our research. In the end, we will provide also as a source, as a possible source for comments and Q&A session at the end, some recommendations for instructional design. So briefly, the research context, I don't know if maybe some of you were present also last week in a previous session on industry competitiveness. The research context is the same. The Italian National Center for Applied Research in the field of big data, high performance computing, and quantum computing has an observatory, which is a project aimed to open the ecosystem of HPC and enabling technologies to a broad community of interested parties. How we do that? We map a lot of use cases of enabling technologies. We develop future scenarios. We provide advice to policymakers, but of course also we reflect on the issue of education and training in such advanced matter that of course poses challenges also in this respect. Practically, the project has collected more than 250 use cases of high-performance computing application in different industry domains. We have presented them in 14 thematic reports and articulated on 5 main sectors. Just a quick introduction to say that you find these reports almost all in double language. So you find also the English version on the website of the Observatory project. But let's dig deeper in the object of this talk, presenting you the white paper of the big ideas for HPC education. You find the link in the chat to download it. It's of course free and open to read to anyone is interested. So what do you find? Of course, is you see more than 80 pages report. So we have not the chance today to cover in 25 minutes, half an hour, all the contents of this report. But I want to spend 1 minute in order to give you some insights on how to read it and maybe focus your attention on something that it's more related to your work and to your current professional challenges. So we start by formulating a sort of state-of-the-art in HPC education, identifying the core competencies and curricular guidelines. We reflect also on the state-of-the-art in K-12 schools, so under 18 high school context. There are some initiatives and we map them. Then we focus on higher education and then on training for professionals on the job. Then after the state of the art, we discuss existing initiatives in Italy and Europe on HPC education. Many of these activities are probably projects in which you are involved. And so we hope that you will recognize yourself and your institutions in this kind of state of the art. After this introduction part, we then focus on the framework of the big ideas, starting from the concept of big ideas in science education. Of course, Michael Lodi will cover in a minute the issue of the framework, the framework elements. And then to give you a sense of our research, then we of course present our research methodology, which has made which has been built on literature review, on expert consultation, and on a questionnaire-based survey that we delivered in more than 1 year to many stakeholders, and that allowed us to write the results and discussion and conclusion of this report. The results session, we will present them in this webinar, is articulated in a first subchapter on the emerging needs and training gaps in HPC education, then the presentation of the 10 big ideas that we identify for HPC, and we conclude with some recommendations for instructional design that we think that can inspire further design phases for many different programs, both for academia and industry. So this is the report. This is the table of contents. We hope that you will read it and you will find something interesting. So, as I said, I start now to show you the gaps that we identified through our research, and that are of many kinds. We found some transversal skill gaps and conceptual gaps that are valid for different stakeholders, and also to different backgrounds that these students or learners in the field of HPC have. So a transversal skill gap is that the foundational HPC skills are usually largely missing in curricula. So parallel programming and the principles of HPC system architecture are often treated as advanced topics or elective ones rather than fundamentals for the computer science teaching. We have gaps in the software optimization. We have a very well-described deficit in the so-called data-intensive computing. Few curricula cover parallel I/O, data locality strategies, or storage hierarchies in sufficient depth in order to build actual competencies. Then we have a difficult problem in understanding the concepts behind the HPC environments. So there is a sort of misconception of HPC clusters as simply bigger laptops. And so the expectations are especially from professionals, often misaligned to the actual reality of HPC environments. We have still a gap in the integration of AI and data analytics, while it's very important that especially professionals can be fluent in both paradigms of this type. Finally, as the last transversal skill gap and conceptual gap that we identify, emerging technologies are still underrepresented in training. So training on heterogeneous computing, but also cloud-based HPC, containerization technologies, and more frontier topics are still absent in many training proposals and training projects in the field of HPC education. These are transversal skill gaps, but then we go on in our report, and thanks to the survey and to the expert consultation that we performed, we tried to identify the training gaps depending on the background that students or learners have. For example, in this slide, you see the difference in the gaps between students and graduates with a computer science background, and on the other side, the training gaps considered for students and researchers also in we call domain disciplines, so not computer science students that specialize in a field for which HPC can be valuable in order to obtain further innovations or solid advantages. For computer science, I go very briefly on this kind of activity of results, so that you can also explore better in the white paper or in the Q&A session about the computer science students. We have a recognized lack of core HPC integration, again, insufficient optimization skills, weak exposure to data workflows, narrow focus on theoretical knowledge with a difficult part of practical exposure, which is still insufficient in many programs that are offered. On the other side, for domain students with a non-explicit computational sciences background, there is low computational literacy, which often hinders the possibility to go in depth with HPC training. There is an over-reliance on domain tools. There is a problem of the so-called bridging gap, so the insufficient skills on programming, on data structures, on scalability concepts. But there is also a problem that training is always or often offered lacking a contextual training. So HPC foundation for domain students risk to be too theoretical or too generical without going in depth on the possibilities and the potential for the specific domain of interest. Another kind of differentiation that we do is the difference of training gaps on one side for academic people, educators, students, and researchers, and from the other side, industry people, professionals, and practitioners. Of course, there are common issues, but we have on the academic side, curricula, fragmentation, an educator preparation gap. There is an issue of reproducibility, which is often underemphasized, late exposure to HPC context, and there is a limit on infrastructure access. On the industry side, there is a need for more foundations that can help the understanding and discovery on the field of HPC. There is an issue of training formats that are not always recognized as meaningful and compatible with industry needs, but also issues of upskilling, continuous upskilling, of certification gaps, knowledge transfer weaknesses between also the same industry, and access to HPC challenges in order to have more practical side. So just before leaving the floor to Michael, in order to present the framework of big ideas, I close this gap session. Identified that there are cross-cutting issues that have been claimed by all the experts that we have interviewed and all the literature review that we have analyzed relating to the emerging technologies, which are usually underrepresented still in the field of HPC education. There is an issue and a gap, strong gap on data management and governance, a lack or a need from the other side for a more focused training on sustainability and societal impact of HPC, a need for more interdisciplinary communication, and also a need for a new, probably, or a more solid pedagogical method in the field of HPC education. So I close now my slide sharing, leaving the floor to Michael for the presentation of the framework that we chose for our research.
Okay, yeah. Thank you. Thank you so much, Eleonora. So, I would like to spend, as I said, some time to give you this idea of the big ideas framework before actually talking a little bit about big ideas of HPC. So, what is the big idea? The big ideas arise in the natural science education. And a nice definition that I like is the key ideas the students should encounter in their science education to enable them to understand, enjoy, and marvel at the natural world. Okay, so this is how big is a big idea. It's something marvelous about our world, our natural world. So they are not general principles, subject areas, curricular topics. The a common error is to list some topics instead of big ideas, but a way to capture the essence of the discipline, that really what's at the core of the discipline. So not a sequence of topics, not necessarily in sequence, is what students should take in, should remember when all the technical details has been forgotten. And usually these concepts are fundamental to the discipline, but not obvious to the layman. Okay, so some languages maybe big ideas is strange, that the word big is not very well clarifying. So someone suggested to call them powerful ideas of the discipline of a discipline. Um, so it's a way to avoid that students or practitioners or whoever learns something new perceive science or a topic as a disorganized set of information with little meaning. Um, so it's for teachers, for educators. I like to call them beacons to guide them to not get lost in the sea of details. Of course, the details must be taught. You cannot go and teach directly the big ideas. The big ideas will emerge from what students learn, but the teacher should have in mind that this is the direction in which they are guiding the students. And so the big idea can guide the choice of inclusion or exclusion of a topic, for example. It helps to focus on long-term knowledge, which especially in computer science and especially in technical fields like this is not easy. Um, and of course, on the other hand, can enable non-technical people or non-computer science experts, for example, in HPC, to still imagine application use cases even without knowing the technical details in some sense. Okay, so can have this double aim. So to be concrete, because this is quite abstract for the moment, these are the proposed 10 big ideas of natural science. All matter in the universe is made of very small particles. Object can affect object at a distance, or let's take the number 6. Our solar system is a very small part of one of the billion galaxies in the universe. So look at the marvel of these ideas. Okay, organisms require a supply of energy and materials for which they often depend on or compete with other organisms, and so on and so forth. Of course, it's not just a list. Every big idea has a digging deeper, an explanation, and maybe they have a short one like this one, and then a longer one, also a different level of details for different also educational levels, for example. Then there are the ideas about science. So let's try to move from natural science to computer science for K-12. So another important framework is the computer science big ideas for K-12 education. And if you see them, some of them may be also big ideas of HPC. Information is represented in digital form. Algorithms interact with data to solve computational problems. The performance of algorithms must be modeled and evaluated. Digital system create virtual representation of natural and artificial phenomena. Digital system communicate each other using protocols. Time-dependent operation in digital system must be coordinated. So already some aspects of HPC are of course present in the big ideas of computer science. Of course, now someone tried to design the 5 big ideas in artificial intelligence. Personally, I want to mention this just because it's a thing on which I've worked on a lot, and that really gave me the idea of what is a big idea. You can securely generate a shared secret by only communicating on an insecure channel. The related topic is, of course, Diffie-Hellman key exchange, but as you can see, I didn't say Diffie-Hellman key exchange. This is the topic, the things that students will learn. But what's the powerful idea behind that? I can talk to Eleonora now, and we can generate a shared secret communicating on this insecure channel because you all are all listening. So this has a huge impact in the world. Think about the pandemic without this kind of cryptography that allows us to buy stuff on Amazon without worrying about our credit card and so on, and without never meeting the Mr. Amazon in person to share a secret, and so on and so forth. So this is the impact. Of course, it's not easy to design big ideas for such a technical topic like high performance computing, engineering topic in some sense. Okay, so of course we design a proposal, but we are more than open. So this is the first version, but we are open to comments, to feedbacks, to proposal for other big ideas, for proposal for removing some big ideas, and so on and so forth. So this is not a complete work, of course. I don't have time to go into the details of each big idea, so I will try to present some hints, but my suggestion is like 10 pages of the report, 10 big ideas of HPC. Look at them, think about them, and then I will share a link with you to give us feedback, and that would be hugely appreciated. So the first one is, of course, that computation has physical limits, and HPC can help us push them. Okay. Computers are physical objects, so they are limited by energy, size, components. And since the 2000, we could not simply increase clock frequency, so we had to add many cores, more machine in parallel, and high performance computing means exactly to push this limit, to go beyond the standard computer everyone has. And of course, this limit today is also limited by energy efficiency, so by sustainability concerns. The second big idea, which is the most cited one by people that answered our questionnaire, is of course parallelism. Is the main way to get more speed and more scale. We have to do many operations at the same time. Inside the core, we have single instruction, multiple data, vector unit. On a chip, we have multiple cores. Across the system, we have many nodes in a cluster. And of course, we can parallelize data, applying the same operation to many items, and also parallelize tasks, run tasks in parallel. And of course, this adds new problem: coordination, communication, synchronization, load balance, and so on and so forth. So, for example, emerged a lot of design pattern, parallel design pattern, common strategies for organizing parallel computation. The idea 3 and 4 talk about decomposition. First of all, we have to match the algorithm and the architecture. There is no best algorithm in isolation, let's say. Maybe an algorithm is elegant, in theory, is clear, but it ignores memory hierarchy, the network, the parallel structure of the machine. So there is this co-design approach. A parallel version of a serial algorithm is not enough. And for example, maybe an algorithm that does more computation but has much less communication is better. So the problem is to decompose the problem in smaller parts. Of course, you can decompose data, subdomains of a grid, different rows of a matrix, but also tasks, different stages of a pipeline. And of course, the decomposition must be balanced and minimize communication. But this is the core, because for decomposing of the problems of HPC, because for decomposing you need both computing knowledge, knowing the machine, knowing the algorithm, but you also need domain knowledge, and that's where people at the intersection between computing and the domain expertise come into play. We call these boundary people at the interdisciplinary people, okay? Because to decompose the problem, you also need to have domain knowledge, of course. Of course, as I said, communication can be more expensive than computation. Okay, and so reducing data movement is important. Again, also the hardware is important. So in the co-design, there is one idea about the software part, and the idea 6 is the idea about the hardware part. The modern HPC systems are heterogeneous. They consist of CPUs, GPUs, hardware accelerator. They have different execution model, different memory access. And of course, the open problem at the moment is performance portability. We would like to have code that runs reasonably well on different architectures without rewriting the entire system. This is what happens today with standard computers. We just write Python, and most of the time is fine on every computer. But this is not the case in HPC. But HPC is not just a niche thing. It is today at the basis of many fields: climate sciences, astrophysics, material science, genomics, medical imaging, just to make examples. Industries use this for finance, manufacturing, logistics, and today AI, large language model, they depend on this. And the scientific research really depends on this. Today, after theory, experimentation, simulation, the data intensive science is called the fourth paradigm of science. So HPC is exactly what supports this approach. The big idea 8 is really the most scientific one, because it says that there are theoretical limits. Not all problems scale well, even with good hardware. Of course, a classic result is the Andal law. A small serial part can strongly limit the maximum speed up, no matter how many processors we use. But fortunately, there is also the Gustafson law, that tells us that, okay, if we have many processors, solve a big problem, and you will solve it hopefully in roughly the same time. So each processor gets more work, and we can scale. So, of course, these are related to what is called sometimes strong scaling with fixed problem size and weak scaling with bigger problems. Of course, the algorithmic structure to our solution is one of the main bottleneck. The other idea also tells us about science. It is reproducibility. Using of open source tools, version control is fundamental to make to use the same code version, use the same library, to use the same input, same parameter, well-documented workflows. Helps us having reproducible computation, reproducible experiments. And of course, one example is the problem with floating point arithmetic that even with the small errors can at large influence a lot scientific results. The final big idea is a very general one, and is the fact that while students learn HPC, they can practice ways of thinking that are useful in many contexts today. Parallelism, decomposition, cost of communication, performance models are crucial not only in HPC, but also in cloud computing, in big data analytics, in large-scale AI, in hybrid system like the quantum and classical workflows. So the big ideas can be, the HPC can be a way to train also for other domains. As you can see, I presented these big ideas as very technology independent because the aim is to be long lasting, to be long-term knowledge. But of course, limit of computation, parallelism, co-design, decomposition, communication costs, scalability, reproducibility, transferable skill will, we believe, be relevant for a long time. So again, I really skimmed them. The suggestion is to visit the report, and for any feedback, for suggesting new big ideas, please visit the link that probably Eleonora is sharing in the chat, or you can scan the QR code and answer the question to help us refine this list. And I will I will give floor back to Eleonora for some recommendation and conclusions.
Yes, just a brief conclusion before opening the final section on what we extracted as possible recommendations to inspire further instructional design on these issues. In these slides, I have summarized what we described in more depth, of course, in the white paper. So first of all, university is asked to embed HPC fundamentals across relevant degree programs rather than treating it only as a specialized elective course, but also ensuring an early exposure to parallel thinking and computational literacy. We recommend to adopt what is our big ideas approach in order to create a structured but also coherent curricula that can emphasize enduring principles over transient technologies in HPC training. Building capacity through HPC education communities of practice, faculty training workshops, and shared teaching resources addresses a shortage of qualified instructors, while on the other side, ensuring access to hands-on HPC environments is essential for an experiential learning to understand scalability, performance optimization, and also system management. Another issue that recommendations emphasize is to tailor training to different learners' profiles while encouraging cross-disciplinary collaboration. So it's a mixture, of course, recognizing that computer scientists need domain exposure while domain scientists or domain profiles need computational foundations in order to collaborate effectively in the implementation of HPC innovation. We recommend to strengthen the connection through also between academia and industry through internships, joint projects, and with also the involvement of industry experts in the curricula. As in the rest of the white paper we have discussed, the approach should integrate more data management, AI governance, sustainability considerations, and in general emerging technology and innovation trends, meaning quantum computing, quantum technologies, digital twins, to prepare the professionals for the converging computational landscape, while supporting also diversity initiatives to provide multiple entry points for learners with varying backgrounds, ensuring equitable access to training, resources, and opportunities. So these are our recommendations for the white paper. Of course, as I said at the beginning, but also Michael remarked, comments and contributions are more than welcome. We have prepared a survey, but feel free to contact us in order to share also in a different form your comments, your insights, and possibly also some reformulation of what we presented today and what is present in the report. So thank you very much. I stop slide sharing and I say that from our side also the slides can be made available to the audience in order to have this brief summary, but you find all the content explained in much more depth in the white paper. Thank you.
Thank you.
Michael, you want to add something about this methodological part?
Yeah, no, I can add something for what concerns big ideas because it's exactly, I mean, the way they are suggested is really with open discussion, long discussion. So the main thing is that I presented in many different contexts, maybe like at a conference, in the meeting of the Observatory that both me and Eleonora are part, and also that Eleonora is managing actually, and also like one-to-one, we did 3 long interviews with 3 university professors, or 2 university professors and 1 EuroCC expert actually. So the point is really that I presented the idea of big idea in general. I gave them the list of the example, and then through discussion they were like brainstorming, saying, giving us examples and so on, and then we also with our personal study of textbooks and so on and so forth, because in many textbook introductions, for example, authors sometimes try to give the big ideas before going into technical details. So, and that's how we constructed this. So it's more like that we learned a lot about HPC, we talked a lot about expert, and then we summarized the main points that were recurrent in all these 1 year long discovery, or 2, maybe almost 2 years long discussion. So this is why it's not is a really grounded theory, qualitative methodology. With this idea really emerged from discussion. So this is the main approach, at least for the big ideas.
Great. I'm writing another question in the chat. Meanwhile, please feel free to use the chat for your question, or you can raise the hand and ask. I would like to ask, what is the most challenging idea that you think would be?
Yeah, I would not. I can answer Eleonora, and then maybe also Eleonora. She focused on the recommendations, so she can for sure integrate more. But I believe that the point is that HPC as a C, as a computing element. So, at least for example, in Italy, not many people are studying computing in their school career, even. Like in the next year, we're introducing it for the first time in school curricula in K-12 education. So, most of the people, most of the physicists, most of the astronomers, most of the biologists, most of the physicians don't even have any basics of computing. While, for example, they all studied math at least for 15 years of their life, good or bad, in good or bad ways, but still have an idea of what math is and can do pretty advanced math for high school, for example. And so this is the point that at least some basics of computer science are needed for every expert to really understand what they are doing. You cannot start designing an HPC system without having the basics of algorithm and so on. So I believe that before the big ideas of HPC, there are the big ideas of computing, because without them, it would be a huge challenge to introduce them. So I believe that the work is even before HPC. The other thing is, of course, the the need both for expert in computing and expert in the domain. If you don't really understand the domain, you cannot meaningfully decompose it. And if you really don't understand the system you are working on, even if you are expert in the domain, you cannot. So interdisciplinary work, discussion, teams, and also academia is not encouraging this. If I publish something in the medical domain, it will be ignored for my career. But I can help a physician to use HPC, artificial intelligence, and so on and we work together. It's very beautiful, but not suggested by the academic system. So this is another important challenge, I believe.
Great.
With a shared system to submit jobs, to schedule jobs, and so on and so forth. This is a thing. The other thing that actually was told to us is for sure to use meaningful examples, like when teaching a parallel algorithm and so on, that are engaging and also meaningful for the students, and not too much that does not require too much other knowledges, like the field knowledge. And this is a sweet spot, because from one point, if an example is meaningful, it must be linked to a specific domain, a real domain, and so on. But the other point is that sometimes the difficulties, for example, for computer science students, is to understand the math, the physics, and so you have too much cognitive load, let's say. On this, I suggest some work that is cited in the paper from Moreno Marzolla, which exactly presented the paper in a special session we held. He also won the best paper because we liked it a lot, which was his effort to create a small, meaningful examples, and really meaningful, so not all embarrassingly parallel, because of course it's easy, like really examples that grasp different pattern, that like students feel the necessity, the need of using something that they are going to learn. So these are two aspects that I recall from all the discussion. I don't know if Eleonora want to add something.
QR code, you can like take 2 minutes to give us your feedback. So it's very important for us to improve our sessions. And if you need anything from CASTIEL, from Work Package 3, we are happy to provide. Here, let me just stop the record.